If you need to copy these notes down, what I'm doing is I'm recording this for the people gone today. There's some cross-country people that will be gone today, some softball people gone 8th period, different things going on today. So you could access this, okay? You don't have to copy it down now if you were gone Friday. And what you can do is you can stop playing the video and just write down the notes if you want to. So mass is neither created or destroyed. We show examples that the left side must equal the right side in its weight. And we said that this one needs to be 16 grams. Okay? And so you might have a real simple problem that you'll have to do where you'll have to get the sides to equal out. That should be really, really easy. Okay? Should not have any issues with that concept or that idea. Okay? It's always true. We get into balancing, not this unit or the chapter, but another unit we'll get into. We talked about the law of definite proportions and saying that, you know, when atoms go together, they always go together in an exact ratio. And that exact ratio never changes. Okay, it's kind of like a recipe, but that recipe, you can't get a little, you know, like when you do a recipe, sometimes you don't have to be perfect, right? It says 1 cup, maybe you get a little less than a cup, a little more than a cup, a sugar or a teaspoon or tablespoon. But it's kind of a recipe of how it goes together. And nature automatically sets that ratio. Nature says, this is how they go together, and it's always going to be exact. Now sometimes you can have something left over. Okay? Sometimes you can, if the ratio is not perfect, you're gonna have something left over, and that's called excess. And you always have reactants that's limiting and one that's in excess, and we'll do that later as well. But this ratio would be like 1 to 16. So if you had to predict how much you need of one element that goes with another element, you could predict that based upon the ratio comparison. Okay? And that's kind of what we did here. We went through this example. We said, all right, how could we predict? How could we predict how much hydrogen you would need? So we set it up as a ratio. We said 16 over 2, which would be 8, is equal to 2.5 over hydrogen's weight. And I think we figured that out to be like 0.3125 when we did that ratio. We said 16 over 2 is equal to 2.5 over x, cross multiplied. You got 8x equals 2.5, and then x equals 2.5 divided by 8. Right? You guys can do that? If I gave you a problem and I said, oh, how much of this element needs to go with oxygen, or how much oxygen needs to go with so much hydrogen, you could figure that out because you know the ratio. It's pretty easy math as well. It's a ratio type of problem. All right? Same on that one. You could figure out oxygen. We didn't do it. So, and we got to this one, right? We did this in class. Okay, so we said 1 and 3 would be the same sample. And the reason why it's the same sample is because we would take 3.9 divided by 3.1. And when we did that, we got an answer out that was 1.25. So then we did the same with this one to see what our ratio was. This was 1.25 oxygen to 1 phosphorus. The second one that you would do would be a ratio that would be 1.8 oxygen to 1 phosphorus. That's not the same compound. It's a different compound with a different ratio with phosphorus and oxygen. Okay? And then the last one is 15.6 divided by 12.4, and we get an answer of 1.25. So 1 and 3, like I might give you a problem that says, okay, I've got some samples here with some different weights, which ones are the same? And all you have to do is find the ratio of each one, and if it's the same ratio, you got your answer. You got it figured out. Okay? Because phosphorus can go together like P2O5, it can go together. It can go together as PO4. It can go together as PO3. So there's different ways in which elements can hook together. They don't have to hook together all in one specific way. Now, this one is a long definition. It's kind of, I've got a couple words there, one word there. It's kind of all together, but it should be something similar to what you have in your notes. So that last example with phosphorus and oxygen, we had two different ratios. So all this says is that elements can go together to form different compounds with different ratios. Let me give you a simple example of that. Okay? There's a simple example of that we could look at. CO2 and CO. What's CO2? What do we call that? Carbon dioxide. What's CO? Carbon monoxide. They go to two different ways. Now, when you start your car up and the exhaust start coming out, some of the exhaust has CO2 in it. And some of it has CO in it. And what happens when the fuel burns not perfectly, then there'll be combinations of both of those given off, CO2 and CO. And so oxygen can go with carbon in a different way depending upon the reaction we're looking at. So that's a multiple proportion, right? 1 to 1, 1 to 2. We can also have a carbonate. Well, this has a charge, though, to it. We can have CO3, which is a -2 charge. Don't worry about the charge. But we can have a carbonate. What's that ratio? 1 to 3, right? By how many you have. Not by weight, but by how many you have. Okay? Now, if we wanted to put the weights in there, they should have a ratio as well when we look at the weights. It might come up later. I don't remember the slide. This is from last year, and I didn't have time to double check it. But this ratio here, let me go ahead and figure out the ratios here. If you want to write these three down, you can do that underneath that definition. Now, if you don't have room in your notes because you just wrote definition after definition, you can write another section that says law of multiple proportions and then write these examples down. Okay, so these are by weights. These are 1 gram to 2.6 grams. This is 1 gram to 1.33 grams, and this is 1 gram to 3.99 grams if we had one of them. Now this is constant. It's always nice when you compare data that you have one that is a constant. So our carbon's always 1 gram, and our weight of our oxygen's always going to be a little bit different than that. It's going to be higher than that. Okay? So, it says when the elements form a series of compounds, that's a series of compounds with the same two elements. The ratios of the masses of the second element that combine with 1 gram of the first element can always be reduced to a small whole number ratio. Okay? What that means is that this second weight can be divided into the other weights of the other compounds and give you a ratio. So 1.33 divides into 2.66, and what number do you get out? 2. So it's double the number of atoms, because it's double the weight. Down here, look at this one. This one, 3.99, what's that divisible by 1.33? 3. How many more atoms does it have than CO? 3 more atoms. Okay? So we could go, there's no such thing as CO4, but that would be an example of multiple ratios. Does that make sense? The first one's 1, then the second weights, when we compare the second weights with of 2 different compounds, are always going to be ratios of whole numbers. And that's about it. Okay? Now, this might be repeated here, so wait before you write something down. Okay? So, when we do this, when they're not the same compound, right? Does everybody agree? If I asked you if these are the same compound, you would say no, because the ratios aren't the same. The ratios for carbon to oxygen on this one is 1.3. That's this example here. Okay? And then C12 to 32 grams, that example would be this one here, CO2. So they're not the same compound because they don't have the same ratios. That's like our samples 1, 2, and 3 that we had. Okay, so that first sample, CO, was like on the board over there. It's 1 to 1.32. Okay, so if you already have that down, that's probably better to write that down than what I have up here. Okay, that next ratio I have 2 to 2.64. It's just kind of different rounding that was involved. If the first formula is CO, if this first formula is CO, then the second one has to be CO2. Because it's double the weight, which means it's double the atoms. If it's double the atoms, then we can write CO2. So that's what it's going to be. So that's our law of multiple proportions. Here's another example. Okay? So sample of NO is 1.14 to 1 gram. I'm going to go back. Which of these samples is the same as this sample of NO? Go ahead and figure it out. Which sample up there is the same as NO? Sample 1 or sample 2? What would you do to figure it out? This is a 1 to 1.4, so what you'd have to do is you got to make this your divisible one, because the one that divides in is always going to give you 1. So you take 9.14 divided by 4, and what do you get? 2.3, right? Okay, or 2.29 you get for that one. Sample 2, when you take 10.3 divided by 3, you get 3.43. So neither one's the same sample, right? So if this sample is NO, what's this sample's formula? NO2, because the weight is double. It's 1 to 2.28. Right? So it's 2. It's NO2. This one would be NO3. Because when we come up, it's going to be 1 to 3.4, which is triple this number. That 3.4, I can divide by 1.14, and I'm going to get 3. So it's going to be, when we take a look at it, NO3. Okay? Questions you have with that? Right, you'll get some examples of those to do, but that's called the law of multiple proportions. They're just ratios. You're comparing the ratios. All right, we're going to go to Dalton's atomic theory. And then what I want you in your book, if you have your book, we're going to be looking on by the way, if you're redoing tests, I'm going to give you guys your tests back today because everybody's taking them. You got to do that by Thursday. Okay? Redo either test, and then I've got sheets I send out to you through your Gmail, everybody, for Chapter 1 and Chapter 2, since I was gone all of the week before last. So if you guys would turn over to page 68. 68. So, believe it or not, John Dalton was kind of a Renaissance man. A Renaissance person, if you're a Renaissance person, basically during that time, you studied all different areas, and you were kind of a scholar of a lot of different areas, science and English and history, and a lot of different areas. Okay, well-rounded person. And John Dalton was actually an English kind of professor. And it's kind of funny, an English professor. But he was had strong areas of science. And what he did, John Dalton, is he came up with in 1800s, early 1800s, kind of looked at all the information that was out there and said, this is what I'm going to come up with about the atom. Because they know that there was this particle that was indivisible. That once you got down to a certain point, you couldn't break it down any further. So it was, even Greek philosophers kind of thought about, okay, I've got this rock, I break it apart, I get some pebbles. I start breaking it further down, now I get kind of fine granules. I keep on smashing it. I get powder. How far do you go to where the particles you can't break down any farther? And they came up with this word called atoms. And atoms is a Greek word that stands for indivisible. You guys, we say the Pledge of Allegiance every day, right? Indivisible. What does that mean? Yeah. Nation, our nation, we're going to keep together and stay together, we're indivisible. Okay, our nation's not going to make separate nations, like Texas isn't going to have their own nation, and Nebraska's not going to have their own nation. And we have states, and they have certain rights, but indivisible means, that was the Civil War, North versus South. They were going to break off. And they said, no, we're not going to do that. We're an indivisible country. We're all together, even though there's differences that's involved. So there are, when you guys write this out on a test or a quiz, you will put it in your own words. Okay? You don't want to write it word for word, and you don't want to memorize it word for word. But what you want to do is you want to get some of the major points out of there. So the first one, he said, is that, okay, there is this particle. We're going to call it an atom. And it's extremely small, and it's indivisible. Can't break it down any farther. Okay? That's called an atom. All matter is composed of extremely small particles called atoms. And so if you look at the periodic table, you guys had an element quiz that you did. And on that element quiz, you had to represent the name or the symbol with one another. And each one of those symbols represents a different atom. And when you break that element down to its smallest part, that atom will have a certain number of protons in it that's specific for that element. It'll have so many electrons and so many neutrons specific for that particular, we could say, isotope. Because each atom has some different, what we call isotopes. Now, it wasn't known of it at this time, but later on, there's enough information that was gathered that some of this theory is not perfect. Now, we said theories can change. Laws, they're really tough because they're pretty much indisputable. Because the math is always going to back it up. So those three laws we went through is pretty much indisputable except the law of conservation of mass. And that takes an extreme situation for that not to be correct. Okay? So if you look in your book, we're just following along on your book, Dalton's Atomic Theory, page 68. They have the same properties. Each of those atoms have the same properties, same boiling point, melting point, density. I mean, when you take a look at the chemical properties, they're still going to be the same reactivity all the way through. So that was his first part of the theory. So we break it down into 5 parts. The second part is that says atoms of the same element are all identical. How are they identical? They're identical in their size, how big they are, how much they weigh, as well as other properties. And then he also said if you got atoms of a different element, like strontium versus barium, they're going to have a different mass, and they're going to have a different size, and they're going to have different properties. And in parentheses I put false. So there's this thing called isotopes. It's a definition you guys should have down. Is that one of your definitions? Isotopes are atoms of the same element with a different weight. So copper has 2 isotopes. It has an isotope that's said to be, we call it copper 63. And then we have another isotope for copper that's copper 65. And they have 2 different weights. 63, copper 63, by looking at the 63, we know its weight is lighter. The copper 65 is heavier. Okay? So what causes a difference in their weights is called neutrons. This thing called neutrons. But it's not the protons, because if you look up on your periodic table, copper is element number 29. And element 29 has 29 protons. So that 29 represents how many protons are in the nucleus. So each of the atoms of the isotope copper 63 and copper 65 have the same number of protons. They have, copper 65 has 2 more neutrons than copper 63. Because that is its mass number. Copper 63, the way we write it, would be how many protons and neutrons are added together. Okay? And we'll get into that tomorrow, talking about those concepts, those ideas. Any questions on the second one? It is a false statement. He said every element of the same atom are the same. That's not true. You guys know twins? So what are some of the twins you know that are identical? Ras twins? Can you tell the difference? If you're around them, do you think anybody around the Ras twins very much? Can you tell the difference? Sometimes? Can you? Yeah, there's certain features that you can pick out, and they're not identical, right? And they're not identical. Even though somebody not knowing them and look at, who else is a twin? Seepers, right? Huh? Well, they're not twins. Triplets. Okay? So, can you tell the Seepers apart?
Yeah.
Okay. You say easy, huh? The best looking one's in here too, so you didn't know that. Okay? How about some other twins? What's that? Monica and Jessica. Cool. Okay. They're hard to tell apart. I have them in class. Okay. So, but if you're around them and know them, then you're going to be able to pick out certain things. Then you know they're not identical. Okay? And that's like atoms. They look a lot alike, but they're not identical. All of them. Number 3 is false. This is another false statement. He said, you know, atoms, once you get down to that point, it's going to be impossible to subdivide. It's going to be impossible to create. And it's going to be impossible to destroy. Not so anymore. We have this thing called nuclear fission. Splitting of atoms. We did that and worked with that in the Manhattan Project. In creating an atomic weapon in the 40s. And when they split an atom, there's a lot of energy associated with it. Okay? They do it controlled-wise. Nuclear fusion is what the sun does. The sun will create all the energy that we get on a daily basis. It's caused by nuclear fusion. And it's taking a hydrogen atom and fusing it together with another hydrogen atom and makes a helium atom. When that happens, you get a lot of energy out. Okay? And the mass of that atom, it becomes less. And so we have that idea of conservation of mass, says that, you know, it's always conserved. Well, if you combine 2 atoms together, their weight, the total weight will become less because it gives off energy, and that's due to the loss in weight. So we got fission and fusion. Right. We've been studying this, haven't we? This idea, number 4. Atoms of different elements combine in simple whole number ratios to form chemical compounds. H2O, H2O2, CO2, CO. Atoms of different elements combine in simple whole number ratios to form a chemical compound. So the law of multiple proportions kind of show us that. The law of definite proportions kind of show us that. And so they started looking at the masses and how they were all ratios when we have different compounds with same elements but different ratios. They were looking at, oh, that makes sense. They're probably these individual units called atoms that are combining, and they either double their weight or triple their weight, and that's called atoms of different elements will combine in simple whole number ratios. And then the last one, when I show it to you, has to do with chemical reactions. Now we know everything goes through a reaction of some sort from time to time. And when it does, those atoms will kind of separate out. They will rearrange into a different formula and give us a different product out. So what he's saying is that when a reaction happens, since mass is conserved, all atoms do are rearrange into different ratios, but we have the same number of atoms rearranging into different products. And so that kind of proves the law of conservation of mass, this last statement. When we have chemical reaction, the weights are the same on both sides. Why? Because all atoms are doing is separating, rearranging, and combining in a different way. Okay, that's all they're doing. So if you have Legos or just something like that, you can put the Legos, take them apart, and put them together in different, and they look different from time to time. If I give each of you like 10 Legos, and I say, go ahead and put those together, I'll probably have 10, or how many ever's in here, 16 different combinations. But all you did was kind of rearrange them and form them into something new and different. Okay? So questions with that. So just real quick, I know some of you didn't get them all copied down, maybe you did. Number one, and you don't have to put these in any order when you describe these on a test or a quiz. You can just say, number one, everything's made up of small particles called atoms that are indivisible. You can put it in your own words. Number two, you can say atoms of the same element are exactly the same. And atoms of different elements are different in multiple properties. You could say that. That would be fine. You don't have to do it word for word. Number three, you could say, that one's kind of hard. You're probably going to have everything in there. You can say atoms are going to be broken apart. They're going to be reformed. Or I'm sorry, that's the next one. But atoms can't be really created or destroyed. You don't even need to subdivide it if you don't want to. You can say atoms, you can't create atoms and can't destroy them, and that's false. You can't. This is one that you can just say atoms combine to form compounds of simple whole number ratios. And then number five, you can say when you have a reaction, all they do is separate, rearrange, and form something new. And I didn't do it word for word. I just put it in my own words and included some of those important words in that description. All right. You guys, thoughts on that? So, what we basically went through is that first section where it talks about Dalton's atomic theory, laws, and how to use those laws. When we look at law of conservation of mass, law of definite proportions, and the law of multiple proportions on that. And this is one of those days where it seems like we take a lot of notes and it's pretty boring and that, but at least you have them down. You've heard them before, and it's not a big issue when you have to go back and look at that to study in the future. I think the next thing that we'll do, starting tomorrow, somebody had already come up to me and asked, what are we doing tomorrow? I'm going to be gone. We're going to take a look at page 77. You want to turn over there. And you have some definitions there. I said I would look at definitions today. I'm going to look at them tomorrow. So, page 77, we start looking at atomic number. That's, by the way, the atomic number is on the periodic table. That's how I identified the elements you guys needed to know. That's the number of protons that are in an atom. That's called atomic number. The mass number is not given to you on the periodic table. So, when you look at the periodic table, you will not get a mass number off the periodic table. Okay? Because it's like the copper 63 and copper 65. Copper 63 is a mass number that tells you how many protons and neutrons it has in it. And copper 65 is a different atom of copper, which has 2 more neutrons in it. So that's why they call it copper 65. But you don't see copper 63 or copper 65 on that. All you see is an atomic mass of 63.54. That's all you see. And that's called the average atomic weight. Okay? So we'll talk about neutrons, protons, and electrons. And you'll have a little worksheet that goes with that. And then we'll do that tomorrow. Okay? Not really many notes, just problem solving and going through some of those ideas. Okay? If you don't have your terms done, you can work on those, get those done. If you have them done and you're not going to be here tomorrow, then you can show them to me and I can go ahead and mark them down now. If you're going to be here tomorrow, know that. Then we'll wait till tomorrow to get those taken care of.